Hey everyone, and welcome to this video about the carbonate system. So what am I gonna talk about? I want to calculate the pH of a solution in an open system with some dissolved carbonate species, so carbonic acid or CO2AQ and bicarbonate, carbonate, as well as hydrogen ions, so hydronium and hydroxide. What is the main difference here between closed system on the left hand side and open system on the right hand side? So the closed system usually refers to a system where there is no interaction with the atmosphere or with the air above the water. So the DIC, the dissolved inorganic carbon, in this system is constant, whereas in the open system it can change. And what I'm gonna calculate, I want to find the equilibrium solution, so where the flux of CO2 out of the water and inside the water are equal, so no change in the chemical composition of the water anymore. I want to calculate for this case for the given partial pressure of CO2 in the air and the temperature and the total alkalinity, so the acid buffering capacity of the water. I want to calculate the pH of that solution. So I will do it from top to bottom. So first we will think about the air. What do we need to know about the air to describe and to find this pCO2 value here? So therefore I'm gonna make use of Dalton's law of partial pressures, which is basically describing that for ideal gases the total pressure is the sum of the partial pressures of all gases in the system. So for our atmosphere, if you take the partial pressure of all gases together, you have the total pressure of the atmosphere. So for example oxygen, nitrogen and CO2 and so on. But yeah, as we are talking about carbonate system in this video, I'm just going to focus on CO2 partial pressure because this is the reactive gas forming the carbonic acid. So with this simple equation we can calculate then the partial pressure of CO2 in the atmosphere. So we just need to know the mole fraction of CO2, that this is the value you usually find in the media or online. So like currently 420 ppm. So moles of this gas divided by the total number of moles for a certain volume. And then we need to know the total pressure of the atmosphere. And with that we can set it in and we get the partial pressure of the gas, so the partial pressure of CO2. For our given atmosphere, currently 420 ppm, so ppm parts per million, so 420 times 10 to the power of minus 6 for this ratio. And then you can look up the standard pressure of our atmosphere also on Wikipedia. This number, just multiply this number in Pascal with this ratio, which just has no unit, and then you will find out the partial pressure of CO2 in our atmosphere currently is 43 Pascal. Okay, so the next step. Now we know the partial pressure of CO2 in our atmosphere, in the air. But how is it going to dissolve in the water? Therefore we use Henry's law, which is basically describing the relationship between the partial pressure of a gas above a solution and the concentration in the solution. So higher partial pressure, more solubility, so higher concentration, which we see on the left here. It's low system, low pressure, so less dissolved gas in the water, and here on the right hand side high partial pressure, more dissolved gas. And unfortunately, this is not a real constant, so it can be described by that, as simple as it is. So Henry's law constant is just the concentration in the water divided by the pressure of the gas. But this is no constant because it's temperature dependent. So look at the temperature dependence. The temperature dependence can be described with the Van Hoff equation. When integrating this, we get a relationship of the temperature and the Henry's law constant. AB, some constant, an exponential, or we can use this expression, which uses another approach. It's basically giving the Henry's law constant with a reference constant at the reference temperature and the actual temperature. So you take this number here, 2400 Kelvin, and you have here your temperature in Kelvin, and this is the reference temperature, and this is the reference Henry's law constant for the given temperature. With this equation you can convert this reference Henry's law constant to the actual Henry's law constant for the given temperature. And you can look up these numbers. It's here, this is a ugly unit, it's cubic meters water, so there's some conversion, blah. So in the end it's like 3.3 times 10 to the power of minus 7 moles per kilogram per Pascal. So that's the unit we want to have, mole per kilogram per Pascal, so that we can just multiply it with the partial pressure of CO2 and get a concentration, mole per kilogram. So what comes next? So when the CO2 is in the water, so then it will deprotonate. This CO2, the carbonic acid, CO2AQ, will deprotonate to bicarbonate and hydrogen ions, as well as the bicarbonate can deprotonate again to form another hydrogen ion and carbonate. So first of all, to describe the system, I'm gonna use this often used simplification, so I don't want to write C for concentration all the time. We will just use squared brackets, meaning that this is concentrations. And then the other simplification, because the CO2AQ, so the real dissolved CO2 that you calculate with Henry's law, and the carbonic acid, they are not really distinguishable. So usually this is used in most textbooks, this simplification, just CO2 in squared brackets, because both species, they react so fast you cannot distinguish them. And then what do we need next? We need to know the dissociation constant of the first dissociation constant of the carbonic acid, basically the deprotonation into the bicarbonate and the H+. So from that equation we can rewrite it, and then we know, when we know CO2 concentration as well as the H+ concentration and the dissociation constant, we can calculate bicarbonate concentration. Then second dissociation constant of carbonic acid, describing how the bicarbonate reacts into carbonate and the H+. Again, same equation, we could rewrite it to express the CO2, the carbonate ion with the dissociation the second dissociation constant, as well bicarbonate and H plus concentration. And last, we need to know the dissociation constant of water, which is called the Kw, which is the product of H plus concentration times hydroxide concentration. And then, just to mention it, this following code will not take ionic strength into consideration, because all these dissociation constants that I showed here are actually pressure dependent and temperature dependent and dependent on mostly ionic strength. So ionic strength is basically just the sum over all dissolved species over all ions together with their charge. So here a small example from this textbook about CO2 in seawater. We have quite different Bjerrum plots for different waters. So here the most crazy example, or let's see, the baseline here for seawater is 25 degree, salinity of 35. This is the black line. So the dissociation constants are where those lines cross. But you see here, there is another extremely shifted dissociation constant. So in another system, which equates to a temperature of 25 degree and no salinity. So then you see these lines. So you see these dissociation constants are always quite different, and it's very hard to determine them. Therefore you need proper geochemical modeling programs. But I'm just going to show the solution for a simple case with assumption of ionic strength 0. So for this case, like salinity 0. So the last ingredient we need to know to describe our system is the alkalinity. So the alkalinity is nothing else than the buffering capacity of the water. So the acid buffering capacity of the water, how much acid it can buffer. For example, if you take pure water, purified water, and you want to introduce some alkalinity, then you could use hydroxides, just metal cation and hydroxide, which dissolves easy. Or you can use carbonates, like metal cations and the carbonate or bicarbonate. And yeah, then the water, if you let it stand for a while, it will find a new equilibrium with the atmosphere. So for the case of the hydroxides, some of the hydroxides will react and neutralize the CO2 that comes in the water and form bicarbonate. And then you can come up with this simplified alkalinity expression. So alkalinity is always depending on the system, how you define it. For example, if you have seawater, you have much more acid-base systems involved there. Or if you have a very dark organic rich water, then you have some organic alkalinities or organic ions that contribute to alkalinity. But this is an example where we just have hydroxides and carbonates that buffer the alkalinity. So it's just the sum over the concentration of bicarbonate and 2 times the carbonate, because it can buffer 2 acid molecules, and then hydroxide minus H plus itself. Because yeah, if you're talking about acid buffering capacity, you need to subtract the acid itself. And then we can rewrite this equation by putting in all the dissociation constants that I have shown in the previous slide. So set in for bicarbonate the expression with the dissociation constant and the concentration of H plus, and then for carbonate set in as well, for hydroxide set in the relationship. So then we get an equation which is basically describing everything as a function of dissociation constants and H plus concentration, as well here as the bicarbonate. So we don't know the bicarbonate, so we're going to use a trick. So we set in the first step again to replace this bicarbonate concentration here, and then we come up with this equation. We just merge this big fraction here to simplify it, and then we get this equation where we know all variables. We know the first dissociation constant of carbonic acid. We know the second dissociation constant of carbonic acid. We know the CO2 AQ from temperature, partial pressure, so Henry's law. And we know Kw, which we can also look up. And we will know alkalinity. And then what we don't know, H+. That's what we want to calculate. We want to calculate the pH. So nothing else than the H+ concentration. So how are we gonna solve it? First set it to 0. So this whole term, alkalinity that we set in, minus this whole term, that should be 0. So for what H+ is this term 0? So this is an equation that you cannot easily solve analytically, so that's why I would use fsolve from Skippy and make it with Python. Okay, and now I'm gonna show you how to solve the system from scratch with Python in my case. So of course you could use a geochemical modeling program like pCO2 or CO2 sys, but then you don't know what's actually happening behind it. For that purpose I created this very simple example to make it possible to still calculate it quite in an easy way, with the simplification that neglecting ionic strength and pressure dependence of dissociation constants. So what do we need? Of course we need to have the total pressure of the atmosphere again, the CO2 molar fraction of the atmosphere. So these days global monthly mean is 420 ppm. So 420 10 to the power of minus 6. Thereby we get the partial pressure of CO2 in the atmosphere. Then we need to know the reference Henry's law constant. In the next step we're gonna calculate from the reference Henry's law constant, href, the Henry's law constant for 25 degree. So multiplying it with the partial pressure of CO2, we get the CO2 concentration in the water, CO2 AQ, which is 14 micromoles per kilogram, quite low. And then we need to feed the program, of course, with the dissociation constant of the carbonic acid and of the water. I copied those constants from the pCO2 database. So actually using for the 0 ionic strength case the same constant that pCO2 is also using. Here the pK values, and then I converted it to the constants. So in the next step I defined for which alkalinity I want to calculate the pH. So I have chosen randomly 5 millimoles per kilogram, and then I defined this error function, which is basically, here we set in the noun alkalinity, the 5 millimole per kilogram, and this is the calculated alkalinity, and we want this function to converge, so to be very small. The error should be very small. And then what you could do, you could solve it graphically, so set in all different H plus values and then see where the error gets very small. But you see here, okay, this scale is quite coarse, but yeah, for a huge range, like from pH 9 to pH 3, it is close to 0. So my approach is to use a numeric solver to calculate the pH exactly. So find the pH at the equilibrium state of the solution for 5 millimoles per kilogram alkalinity and 25 degree temperature and 420 ppm of CO2. So I use Skippy Optimize fsolver. So this function basically needs, I fed the function again and then an initial guess for the H plus concentration so that the program knows where to start, to have some starting point. And then for the given specifications, the pH is 8.87. So with the alkalinity of 5 millimole per kilogram. Then what else could we do? What about the pH of a solution with no alkalinity, so purified water in the equilibrium with the atmosphere? You might expect pH of 7 because it's pure water, but see. So setting in the same, alkalinity equals 0, then defining the function, the error function, and making same initial guess, and then calculate it, and pH is 5.6, and the error is quite small, so it definitely converged. And 5.6, that means the air, the CO2 in the air is acidifying pure water down to pH of 5.6 from 7. Okay, then thanks for listening. Here are my references. So the book CO2 in Seawater, Equilibrium Kinetics Isotopes. I can highly recommend that. It's very detailed and comprehensive. And of course pre-QC version 3. So this is the geochemical modeling program for all purposes. And thanks for listening. And bye.